We are officially halfway through our chapter, and this brings us to section 3.4, which is our linear programming section. Now, what on earth is linear programming? What on earth does that mean? Right here, linear programming is a method for finding the minimum or maximum value of some quantity given a set of constraints. The constraints form a system of linear inequalities, and the graph of the solutions is the feasible region. So I'm going to highlight this here, or underline it. The constraints form a system of linear inequalities. The graph is the feasible region. Okay, this is going to make a little bit more sense when we get into our examples, but again, that's just kind of our idea of what linear programming is. I'm using the wrong paper here, so I'm going to switch out. Okay, here's our key concept, and hopefully having this note sheet will kind of help you as we go through the process, especially as it comes to like not having to write everything down and not having to graph every single thing. Key concept here. If there is a maximum or a minimum value of a linear objective function, it occurs at one or more vertices of the feasible region. If there is a maximum or minimum value, it occurs at one or more vertices. Now, we might have a system of constraints right here. We might have our system of constraints when we're talking about the production of number of t-shirts or production of different things. Maybe we're talking about like a basketball player's performance. Maybe they will do really well until they've played for 20 minutes, but then their performance starts going down. So trying to find their maximum or like minimum cost for a company, things like that. So when we get our system of constraints, we can graph them, find our vertices, and then one of those vertices is our maximum or our minimum. So the graph at this right shows a feasible region. So this little area here is our solution to a system of inequalities. And we are going to just right here quickly write our coordinates at which a maximum or a minimum value could occur. And our little key concept here says that that maximum or minimum, if there is one, is going to happen at a vertex. So our vertices here, we have a vertex at 0, 0. We have a vertex right here at 3, 0. And then the top right corner of our triangle, we could have a vertex at 3, 3. So again, if there is a maximum or a minimum value, it's going to happen at one of these three vertices. All right, so just kind of a quick example too. If you remember our last section, 3.3, we did that problem where we were looking at the vegetable and the meat toppings on our pizza. Our maximum number of toppings could occur at one of those vertices. All right, so problem 1 here, we are going to test vertices. Okay, and we're going to use this graph. So this problem is guided a lot more with that for us. And then our next problem, we are going to actually write our system of constraints from a word problem. We are going to use this graph and the constraints below. What values of x and y in the feasible region maximize p for the objective function p equals x plus 3y? Now, what on earth does that mean? We'll get there in a second. This is our system of inequalities, and again, in linear programming, we call it our constraints. To graph each of these, x plus 2y is less than or equal to 5. Remember, we would want to get this in slope-intercept form. 2y is less than or equal to 5 minus x, subtract x from both sides, and then divide both sides by 2. We'd have y is less than or equal to 5 halves minus 1/2 x. And if you look at our graph, that's what this line is right here. Our y-intercept is 5 halves, or 2.5, and then our slope is negative 1/2. So we go down 1 over 2. Down 1 over 2. And then we keep going. Right here, x minus y is less than or equal to 2. If I try to get this in slope-intercept form, I'd have negative y is less than or equal to 2 minus x. Divide by negative 1, but remember when we divide by that negative 1, we also have to flip our inequality symbol. So negative 2 plus x. All right, so right here, my y-intercept is negative 2, and my slope is 1. Up 1 over 1, up 1 over 1, up 1 over 1. Greater than or equal to, we would shade above. X is greater than or equal to 0 is our vertical line, shaded to the right. Y greater than or equal to 0, horizontal line, shaded above. Okay. So when I graphed all of these constraints, graphed all of these inequalities, this shaded region here is where all of our shaded regions would overlap, all 4 inequalities. Our maximum is going to occur, if there is a maximum, at the vertices of my shaded region. At one of these 1, 2, 3, 4 vertices. Now this p equals x plus 3y, this is just kind of, it's called our objective function. Maybe it's looking at profit of a situation. The profit of whatever is found by taking x plus 3y. So if we're thinking of our maximum profit here, we'd plug each x and y value for our vertex into this equation. That's what we're going to do here. So number 8, evaluate p equals x plus 3y at each vertex. Well, we have a vertex at 0, 0, a vertex at 0, 2.5, a vertex at 2, 0, and a vertex at 3, 1. Plug each vertex in for x and y in our objective function, and whatever gives us our maximum, whatever gives us our largest value, that is our vertex that's going to maximize our, again, if we're calling it profit here. So 0 plus 3 times 0, well, 0 plus 0 is 0. That doesn't really sound like a great situation. P equals x plus 3y. 0 plus, okay, 3 times 5 halves, good practice with fractions here. 3 is 3 over 1. To multiply fractions, we multiply our numerators, and we multiply our denominators. So 15 over 2. And then 2, 0, x plus 3y. 2 plus 0, that's 2. And then 3, 1. P equals x plus 3y. 3 plus 3 is 6. All right, so looking at these, I see the 6, I see this 15 over 2. One of these is the biggest. Let's figure out what 15 over 2 is. Let's see, that's 7.5. This is our maximum value. Looking at our values that we got here, 0, 15 over 2, 2, 6. This is our biggest value. That means our maximum value, our maximized, whatever, our maximum profit happens at this vertex at 0, 5 halves. So to answer our last question, P has a maximum value of 15 over 2 when x is 0 and y is 5 halves. All right, so that's kind of the general idea here. Graph our system of inequalities, find our shaded region, find those vertices, plug them in, and see what gives us the best option, the maximum or the minimum. Minimum is usually if we're talking about cost.